Hello everyone, welcome to our presentation. Today we'll be speaking on our project that we worked on this year, a PPO approach to constraint and control problems. The initial goal of our project was to implement PPO on this system that you see here, the physical ball and beam system. But just a note for now, our main deliverable, our main project sort of shifted over throughout the year into a user interface that could be used by future programmers in order to test PPO on their own desired control problems. So here's just an overview of what we'll talk about today. First, I'll just introduce our project, introduce the physical model that you see, then the computer vision that goes into implementing it on a physical model, PPO, which is the AI algorithm we used, then a part of that algorithm, the reward function, and then finally we'll talk about our main deliverable, the UI. So just to introduce our project first, what are control problems? Control problems are physics-related systems problems where the general aim is to stabilize the system in some form. In the case of the ball and beam problem, the one that we used most of the year, it was the initial problem we wanted to work with. We ended up implementing it on this physical system, and we implemented it through our user interface. The goal of the system, you have a beam with a ball on top of it, and the aim of stabilizing the system is to have the ball roll over into a stationary position at a desired set point on the beam, which can be specified by the users beforehand. The second control problem that we worked with a little bit less, it only appears on our UI as of right now, is the inverted pendulum problem that Dr. Gabor was speaking about. You can see the physical model of that system right behind you. This inverted pendulum problem is a little bit different. Instead of a servo adjusting the angle of a beam here to stabilize the ball at a certain position, the aim of this control problem is shifting a cart side to side with a pendulum attached to it until it's in an upright position and to maintain that pendulum in an upright position in the system. So the general gist of control problems, you're trying to stabilize something. In the case of the ball and beam, you're stabilizing the beam in a flat position with the ball in a stationary position. In the case of the inverted pendulum, you're stabilizing the pendulum in an upright position. So it's all stability that we're working with. What's currently used in a lot of engineering and robotics projects is the PID controller, which stands for a proportional integral derivative controller. This is used to regulate many different things, including temperature, flow, speed, but in our case, with the ball and beam problem, it's the angle of the beam that's being regulated in order to achieve the desired goal of moving the ball over to the desired set point. In the case of the inverted pendulum, this would be used to regulate the angle of the pendulum or the position of the cart that's controlling the pendulum's position. The basics of how a PID controller works is, imagine you have an error function, which tells you how far the current system is from the desired system state. So in the case of the ball and beam, you could think of it as your error could be something like the current position of the ball minus the desired position of the ball, which tells you how far the ball currently is from where you want it to be, right? So if you sum scalar multiples of the current error, the integral of the error, and the derivative of the error, and head in the opposite direction, what you're effectively doing is counteracting the accumulated error in the system in order to shift the system closer to the desired system state, which in the case of the ball and beam is, again, the ball in its desired position with the beam flat. So for some other useful terms you might want to know before we get more deeper into our project, MDP, which stands for the Markov decision process. This is just a mathematical way to model or represent systems like these where there's an environment with an agent that takes an action on the current system state, and there's some response to that action. So in the case of our project, the action could be a change in angle of the beam, and the reaction is the ball either moves closer or farther to its desired point. This MDP is used a lot in reinforcement learning as just a way to represent the problem. And what reinforcement learning actually is it's a form of machine learning where there's an agent, your machine learning model, that takes an action on the environment, and then there's some response to that action. The state of the environment changes in some way, and the agent learns from the reward it gains from taking that action. So for example, if the agents in our PPO model were to tell the ball or shift the angle in some way and the ball ends up moving closer to the desired position, it would be rewarded for that, and it would learn to make decisions more similar to those in the future.
All right, so now we're going to be talking a little bit more about what the physical model is and what went into building and making and the decision making behind the physical model. So the physical model's goal was mainly to have an outlet towards our simulated controller to be able to show in real life that it does balance it and it isn't just all theory, that there's some truth to it in the physical sense. And the main components, of course, are the actual ball and beam, the servo, which is this is the way that the AI is going to control the physical model, which is setting the angle of the beam. The sensor system, this initially was an ultrasonic sensor, and then we switched into computer vision, and we'll talk a little bit more about that in a later slide. And the controller, which in this case is the actual artificial intelligence, or in our case, since we didn't get to that, it would be the PID controller, which Leo described before. So the key objectives would be to be able to measure the position of the ball accurately. So there needs to be a very high degree of accuracy when it comes to knowing where the ball is in relationship to the beam. And adjusting the beam angle to stabilize the ball is the main objective of the ball and beam problem. So we would like to solve that as well. And also minimize the noise and the delay in the system. So there's a lot of noise, like the picture or what the ultrasonic sensor is looking at, and the delay in between when that picture is taken or when that initial state is taken and when the computer is able to make an action. Okay, so for the physical model design, we just 3D printed the actual beam, and we use a servo to change the angle of the beam. The reason why we use a servo and not any other type of motor is because servos tend to be very accurate in terms of their angles. So I could set the servo's angle and not have to worry about whether it is inaccurate or having to re-stabilize the servo. Another thing is that the ball has to be fully free to roll on the beam. A problem that we ran into at the beginning of the project was that we were using a golf ball, and golf balls tend to have divots in their surface, and this doesn't allow it to roll freely. It kind of just wobbles in between each divot. So we don't want that. We want a full smooth ball and a smooth beam so that it can roll freely. And for mounting, we originally, as seen as this picture, we used an ultrasonic sensor. And later on, we decided that this wasn't adequate for what we were trying to do, and we swapped over to a computer vision model. And the servo, again, acts as a control for the beam. So let's talk a little bit more about why we swapped from an ultrasonic sensor to a computer vision model. And here, I want to explain some things. This graph is showing the ball moving back and forth on the beam. And the blue line, the blue graph is telling you what the ultrasonic sensor is measuring. We expect it to be, so this is very zoomed in, but we expect the movement back and forth of the servo to look like a sine wave. But instead what we see is on the blue, where it kind of jumps around. It has sort of that shape reminiscent of a sine wave, but do you see how it like jumps up and then jumps down? This is very problematic because it shows that it does kind of know where the ball is, but not really, as it tends to jump around and spike a lot. So for things that require a lot of accuracy, specifically when we're wanting to match it to the simulation, this doesn't really work out well. So we decided to switch over to a computer vision model. Now here is a more zoomed up picture because I thought it would be better to see, but we can see here that the sine wave is very, very tight in terms of its error. And this worked out a lot better in terms of precision, but there were some trade-offs. So mainly it was the time to process and calculate the position of the ball. Before, when I used the ultrasonic sensor, it was very simple, and that I could just get the ultrasonic sensor data, and that was my position. But with the image, it's not quite as simple, as the image just tells you the position of the objects in terms of the camera, and I need to do calculations for those positions to be able to actually find the position of the ball in respect to the beam. And so that had to be moved over to the computer, which introduced a delay in between when the image was processed and when the action could be taken, which wasn't that much of an issue as I was expecting it to be. So it ended up working out fine. And yeah. So finally, I'm going to talk about what the final system looks like. So this is the general final system of the physical model, and it starts at the actual physical model when you throw the ball in, and then the Pixie Cam, which is what we're using for our computer vision, it takes a picture of the of the state, and it will send it over to my Arduino. And then the Arduino will take that data and it will send it over to the computer. The Arduino is kind of this in-between man between the actual physical model and the computer. And the computer will then run the calculations on both where the ball is, and then it will run a calculation to try to counteract the movement of the ball. And will send it back to the Arduino. The Arduino will then take this data and it will move the circle, and the cycle will repeat until either the ball falls off the beam, or hopefully the ball is able to be balanced to where we want it. So here I want to show you guys two examples of the PID working with an ultrasonic sensor. And here the ultrasonic sensor also had a lot of dead spots, so it's very close to the edge of the beam. But you can see that it did balance it, and then you can nudge it. Eventually it'll balance it. Also notice that the ball is banging into the edge of the beam a lot, and this was a problem because that just made it easier for the beam to balance the ball. And now we're going to show the computer vision approach, which is I think it's much better, and it doesn't really tend to touch the beam as much.
Okay, so now we're going to talk about the computer vision approach. So originally we had an original approach where we implemented Huff, circle, and line detection, as well as a checkerboard calibration system. And the purpose of the checkerboard calibration system is to pretty much map the 3D actual environment with a 2D image, right? You can see this checkerboard image calibration employs a lot of different perspectives, but since the program knows the size of the checkerboard, how many boxes there are, it'll be able to map it correctly. And then our Huff and line circle detection, if you have not taken CV, is essentially just converting our image to black and white, and then taking the edges of those image. At each edge, you can put different points, and from those points you can expand them. And where all these curves intersect is most likely there's most likely going to be the center point of an object. So this is how it works with a circle. Overall, while it did work, we found it to be quite difficult to use because we would have to drape a curtain to the background of the actual system, as well as the fact that it would also detect irrelevance lines that weren't a part of the actual system. So instead, what we chose to use was a PixieCam, which uses color signature detection. A PixieCam is a commercial video camera that you can buy from anywhere. But essentially, the way that this detection works is through color signature detection, which essentially allows the Pixie camera to scan each frame and look for large continuous colors of which it has been trained on. So it saves a certain number of color signatures, and from those color signatures, it detects whether there's the same color in that area. So of course, within this, there is the actual objects, the red ball, which we opted to change the color for, as well as a marker on the side, which because of its color is able to recognize these two different objects. So now let's actually talk about proximal policy optimization and what it essentially is. It's a very complicated process, so this is a very shallow level of understanding, but essentially what happens is it employs two networks, an actor network and a critic network. The actor network uses a stochastic policy and essentially returns a distribution of the actions which can be taken by the policy. And the critic network essentially evaluates how well those actions have been chosen. So within the actual methodology, what happens after these two networks interact is that the action is taken, or a distribution of actions is taken from the actor network, and then those actions are applied to the actual physical system, and essentially we simply watch the system and take in the resulting values through an environment tuple up here, right? We record the different values of the state, such as the acceleration of the ball, the velocity of the ball, the velocity of the beam, the actual beam angle, and then from that we feed this into our policy, which is essentially encapsulated through this equation, which looks very complicated, but don't worry, right? We tried to optimize the objective through this equation, and the only thing that you really need to understand, or the most important aspect, is the clipping, right? The clipping essentially prevents the policy from progressing too ambitiously. So let me tell you a story, right? I took this picture myself at Zion National Park at Angel's Landing, and I saw the end, and I was very ambitious. I wanted to progress forward. I saw that moving along the trail worked so far, so I'm going to keep on doing that. But as I moved through the trail, I fell off to one of the sides, and here I am telling a story now. So essentially, what you can get from that metaphor is that if you're too ambitious with your policy, if you choose to follow the same policy, it prevents you from adapting and actually solving the actual problem. So after this policy is implemented and executed properly, the actor and critic networks are updated. The actor network uses gradient ascent to optimize the following policy objective, while the critic network uses gradient descent to minimize error. So this is a PPO diagram, right? In case you didn't really understand what happens, here is our actor-critic PPO. Here is our environment. The action is sampled from the actor network, which is then fed into the environment. Then we can take the trajectory or the environment tuple and feed that back into our actor-critic PPO, which then gets fed into our critic model and actor model. Then you have these variables which you saw in the last equation, but you don't need to worry about. These were then fed into our clipping function, which goes back into the PPO.
The next thing we'll talk about is another fundamental portion of PPO and other reinforcement learning algorithms, the reward function. What is a reward function? So the agents involved in reinforcement learning algorithms need to know what is considered an advantageous position in the system that they're operating through. The reward function is a function that approximates what is this advantageous position, which is why it's so important for algorithms like these. For example, if you had a reward function that was defined as simply the position of the ball, so the current position, or just the position taken of the ball on the beam, the agent is attempting to maximize the reward function no matter what, because it wants to be rewarded the most for the actions it takes. So if the reward function is defined as simply the position of the ball, it's going to try to maximize that. So the actions that the agent takes will now be attempting to send the ball flying towards the right, because that's what's going to maximize the reward function defined in that way. So some of the things that we attempted during our initial stages of our project, when we were simply just modeling this system on our computers through a simulation, were playing around with different parameters that we used with our reward function. We took different parameters from our state vector, including the position of the ball, the velocity of the ball, the acceleration, and then the angular velocity and angular acceleration of the beam, and use different combinations of these parameters in order to try to formulate our own creative and effective reward function to approximate what is a desirable state for the environment. So whenever we used these combinations of these parameters, what we always did was we normalized them and we squared them. And the reason we did that was because, imagine position. The position can take a value anywhere from -1 at the very left end of the beam to 1 at the very right of the beam. Whereas a parameter like angular velocity may be able to take values with much larger magnitudes. So naturally, if we are not normalizing or squaring these parameters, the reward function and the agent will therefore apply a lot more weight to angular velocity as a parameter, whereas position is a much better indicator of how good we are doing in terms of the system. Another thing that we tried was an exponential penalty for the agent. So this graph right here shows a plot between the distance from the set point and the reward given to the agent based on its position relative to the desired position of the ball on the beam. Using an exponential penalty like this exponentially punishes the agent more as it gets farther and farther from the set point. And what that does is it further incentivizes the agent putting the ball in a position in the relative vicinity of the desired set point. The last thing we tried was signing, which basically if you can imagine a state position where the ball is to the right of the desired set point on the beam, so it's a positive position, you would want the angle of the beam to also be positive in order to make the ball be rolling in the direction of the set point. So in that way, you can sort of define a framework where you want the signage of the position of the ball and the angle of the ball to agree with each other, because that will tell you that at least the beam is angled in a way where the ball is rolling towards its desired position. So because of that, we tried a method where if these two signs agree, we use one reward function, whereas maybe the angle or the sign of the position of the ball is positive and the angle of the beam is negative. Maybe we swap over to a different reward function because we want to punish the agent or reward the agent in a different way in those situations. Long story short, none of those things worked. No matter what we tried on our simulated ball beam environment, we couldn't get the model to properly balance the ball in a way that we felt was realistic to implementing it on a physical model. The main issue we saw was that since we were giving the agent a continuous action space to sample from, meaning that it could take an angle at any given time step, the agent could pick an angle anywhere between -40 degrees and 40 degrees to set the beam angle to. What the model would do in our simulation was teleport between very large and very small angles, which isn't realistic to a physical model because teleportation does not exist. So the main issue is that our model could not learn to have a smooth transition between beam angles. And the solution to that we implemented after we averted our gaze away from the reward function problems was, instead of a continuous action space, we used a discrete action space, which means instead of the agent sampling from anywhere between -40 degrees and 40 degrees, now at each time step the agent is just deciding, should we decrease the angle of the beam, keep it constant, or increase it. So that made the simulated ball and beam environment a lot smoother in terms of the angle transitions, and it made it a little bit more applicable to the actual environment that we have.
Okay, now we'll talk about the GUI. We don't have a lot of time, so we'll go through it a little bit. So we like to call our GUI a unified framework for other environments. And this is because if any other students in the future are trying to work with control problems, they can just use this GUI and it'll probably save them like months of developing, having to go through all the bugs to create some sort of main framework that they can center their focus on, and then instead of worrying about the GUI and how to run the code and training and all that, they can just have a nice unified framework there. And in our system, in our GUI, we can set the hyperparameters of the system. Then you can also define any reward function that you want to use. So you don't have to go in the code, change all those lines of code, maybe have some bugs. Then you can also interact with the terminal. And this is good because instead of tabbing between your GUI and then your code, and then maybe another tab showing like the demonstration stuff, you can just interact with the terminal in that GUI. And then finally, you can also visualize the training results. There's a graph that comes up and it shows per epoch, per like every set amount of like time steps, it'll see how much the model is improving and whether it's like plateauing or increasing or whatever. And this is all very accessible as well. We have good shortcuts, so you can do this very quickly. You don't have to get your mouse clicking all the buttons. You can just press like whatever hotkeys we have. And when you first open the GUI, you're met with this page. This is where you select the environment that's supported by our GUI or what you can add in. We have right now the ball beam and the cart pole system in here, but you can add in anything supported by OpenAI's Gymnasium package. Now this is our mainframe. In here we have the ball beam system, and in the top left corner we see just a little depiction of what it is. You see the ball and the beam, what you're working with. Next to it you see the training progress, which is the training graph for the training results. And as the epochs continue, as you go through the time steps, you'll see what reward you have and whether you're increasing or you're plateauing. Now if you look at the bottom page, this is our control panel. In this area, we have our hyperparameters. For the ball beam, you can set the set point, the initial velocity, and you're given information about them, like how the units work, how they are measured. Because the set point is a decimal fraction. The initial velocity, this is given in centimeters per second, because it's unrealistic to measure like the speed of the ball and the beam in meters per second, because it's like not even a meter long. And yeah, then to the right of that, we have some more hyperparameters. You can randomize some initial values. We have set point and velocity here. These are very important for training because you're not always going to put the ball at the same. You're not always going to start the ball at the same spot when you're training. So, or if you're not going to balance it to the same spot either. And by randomizing the set point, you can make sure that the model learns to balance it anywhere in the beam rather than just at the center. Next is velocity. When you place the ball on the beam, you're never going to place it with 0 velocity. Oftentimes, it'll have some sort of speed, some random speed. And by including a random initial velocity, the model can learn to balance the beam or balance the ball on the beam from any given velocity. Then we have some more reward weights that I think Leo talked about earlier. This is how much each variable is weighted. So for example, if we wanted the ball to come closer to the set point, we would increase the k value, the scalar multiple of the position. So then the reward function is more incentivized to keep the position low, the error in the position low. Same goes for the velocity and the angular acceleration. Now we have our reward function, the code input. This is a nice little terminal that you can use. You can edit the values in there. You can do whatever you want. And then you can toggle whether or not you want to actually use this, or if you want to just use the default one that you put in the code, or that we already have in the code. So right of that is the terminal. This is where you interact with everything that comes out from the computer, sent to you, so you don't have to alt tab back to your code. And to the very right are the buttons there. You don't have to worry about them too much. You can click them, or you can click the shortcuts. For example, if you want to start the training, you just click Alt S, or you can click the button. If you want to stop training, you can click the stop button, or click Alt P. Next slide. All right, here in the next slide we have very similar thing. This is just an example of what we had for the cart pole system. You can see it's very similar. We have the hyperparameters on this side, code input, the terminal, the buttons, the training graph, and then a little picture about what we're doing. So for the demonstration, we can just see a video of this running in action. Here I'm in my code editor. I'm opening the code. I choose ball beam. And in here, I can toggle all the set point velocity actions. I can change the values for the hyperparameters. Then I want to run the code. I want to train it. So I enter a file name, blank one, to use the default file name system. And from the 2 epochs that are run, you can see the graph is starting to get built. Then I stop the training, and then I start the testing. Now you can see the testing for a different model that we had. Then you can screenshot things, you can pause at any time. And if you want to stop it, you can just press stop. So yeah, that's the code. We can skip this next slide. It's like the same thing but for the carpool system.
Oh wait. I guess okay. Wait. We're gonna now show a live demo of the physical model working. So if you can give me the wonderful. All right, and now we can throw the ball in there. Then the position of the beam where it balances it is around there, and then you can see that I can nudge it around. And if I want a volunteer to come here and then play around with it, maybe throw it in there. Madhav, he would like. Thank you. Applause for him, please. Yeah, just nudge it. You can throw it in there. Try not to, throw it too hard, but. Oh yeah, I guess he's not seeing the end of the other beam. Right? See if I can adjust the camera. My camera, placement isn't the best, but yeah, there you go. There you go.
All right, that's it for the presentation. Thank you guys.
Thank you.